This is a standard Major League Baseball. It weighs about 145 grams. Now, if a professional pitcher hurls this at 100 miles per hour, it carries roughly 100 joules of kinetic energy. When it hits the mitt, thud. You feel it? That is a macroscopic impact, trillions of atoms moving together. But imagine taking all that energy, every single joule of that fastball, and compressing it, shrinking it down, past the size of the leather, past the molecular structure, all the way down to a single solitary proton. Imagine packing the punch of a major league pitch into a subatomic particle. On a cold night in October 1991 in the Utah desert, something hit our atmosphere. It wasn't a meteor, it wasn't a comet, it was a single particle. And it hit with so much force that it shocked the scientific world. They called it the "oh my God" particle, because according to the laws of physics, it shouldn't exist. To understand why this particle broke physics, we have to understand how we found it. We don't catch these things with nets. We catch them with mirrors. In the early 90s, the US Army's Dugway Proving Ground was home to an experiment called the Fly's Eye. It looked like a sci-fi art installation. Dozens of giant, barrel-shaped mirrors pointing at the dark vacuum of space. The Fly's Eye wasn't looking for particles directly. It was watching the air. When a high-energy cosmic ray smashes into the atmosphere, it collides with a nitrogen molecule. That collision rips the nitrogen apart, creating a faint ultraviolet flash. Fluorescence, a blue ghost appearing for a nanosecond. Usually these flashes are faint, barely detectable. But at 1:34 a.m., the sensors screamed. The data didn't show a spark, it showed a bonfire. The computer algorithms rejected the event immediately. They flagged it as an equipment malfunction, a glitch. But the scientists checked the logs. The mirrors were fine. The sensors were calibrated. The sky was clear. This wasn't a glitch. Let's talk about speed. The Large Hadron Collider is the most expensive machine humans have ever built. It uses 17 miles of superconducting magnets to accelerate protons to 99.999999% the speed of light. That sounds fast. It is fast. But compared to the "oh my God" particle, the LHID is a toy. The "oh my God" particle was traveling at 0.99, followed by 20 more nines, percent the speed of light. If you raced a beam of pure light against this particle from Earth to Pluto, the light would win, but only by a distance of a few centimeters. At this speed, reality breaks down. Albert Einstein's special relativity takes over. If you were a pilot riding on this proton, the universe would look very different. Time would dilate, space would contract. From our perspective on Earth, it takes light over 100,000 years to cross the Milky Way galaxy. But for the proton, the journey would take 9 seconds. You could traverse the entire galaxy in the time it takes to tie your shoes. To this particle, the galaxy isn't a vast void. It's a microscopic sheet of paper. So we have a super-fast particle. Why is that a problem? Because space isn't empty. It looks empty, but it's filled with the echoes of the Big Bang, the cosmic microwave background, a soup of low-energy photons. For you and me, these photons are harmless. But if you are a proton moving at light speed, these harmless photons turn into a brick wall. Due to the Doppler effect, they appear as high-energy gamma rays. And when the proton hits them, smash. This collision bleeds energy. It creates a shower of pions. It slows the particle down. This is known as the GZK cutoff. It is a cosmic speed limit calculated back in the 1960s. It dictates that no particle can travel faster than this limit for longer than 150 million light years. If it travels further, the cosmic fog will slow it down. This means the "oh my God" particle must have come from our cosmic backyard. It couldn't have traveled far. Its source has to be close. So astronomers grab their star maps. They trace the trajectory of the particle backwards. They expected to find a violent monster, an active galactic nucleus, a supermassive black hole devouring a star, a magnetar twisting the fabric of space. They looked at the constellation Ursa Major, and they found nothing. The particle came from the direction of the local void, a massive region of space that is effectively dead. No violent galaxies, no super accelerators, just darkness. For 30 years, scientists argued. Maybe it was a fluke. Maybe we measured it wrong. Then in 2021, it happened again. The Telescope Array project detected another ultra-high-energy cosmic ray. They named it Amaterasu after the sun goddess. It was the second most powerful particle ever seen. And when they traced its path, it pointed right back to the void. This leaves us with two terrifying possibilities. Option 1, there are invisible particle accelerators hidden in the void. Dark matter collapsing, cosmic strings snapping like rubber bands, violent events that are completely invisible to our telescopes. Or option 2, Einstein was wrong. Maybe at these extreme energies, special relativity breaks down. Maybe the speed of light isn't the limit we think it is. We are looking at a message from the universe that is written in a language we haven't learned yet. Somewhere out there in the silent dark, something is throwing rocks at us. And until we figure out who or what it is, we are just standing on the pitcher's mound, waiting for the next strike.